Hey all, and welcome back. We're now going to continue our discussion of forces and Newton's laws of motion with the second of three chunks of chapter 4. We're going to be looking now, reviewing Newton's laws of motion and looking at how they apply to various situations and doing a series of sample problems. So let's start by reviewing Newton's laws of motion. Newton's first law of motion tells us that an object in motion will stay in motion and an object at rest will stay at rest unless acted upon by an outside net force. Keep in mind, net force. It's not just any force. All right, look, here's my cell phone sitting on my hand. It's being acted on by a force, its weight, and my hand. But its net force is 0, so therefore it will maintain its constant velocity of 0 meters per second that it has right now. Newton's first law of motion. Boom. All right, so in one word, this is equilibrium. When an object is in equilibrium, what that means is that there's no net force acting upon it, so it is not accelerating at all. So again, this means that the net force, the sum of all the forces, is equal to 0, meaning the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is also equal to 0. Now, Newton's second law of motion. What it tells us is that the net force of an object is equal to its mass multiplied by its acceleration. So really, you can think of Newton's second law as the situation where you do not have equilibrium, when the net force does not equal 0, and instead it's equal to its mass multiplied by its acceleration. So the net force, again, is mass times acceleration, and because it's a vector, we can break it into x and y components. Sum of the forces in the x direction equals mass times acceleration in the x direction, and sum of the forces in the y direction equals the mass multiplied by the acceleration in the y direction. Boom. Newton's third law of motion, lastly, tells us that for every force, there is always an equal and opposite reaction force. A great example of that, as you see in the picture here, is with rockets. How do rockets propel themselves upward? Well, by thrusting or forcing hot gas out the back of the rocket, then creates an equal and opposite force pushing the rocket upward. Cool. So before we jump into applying Newton's laws of motion, we're going to do examples with Newton's first and second law. I want to introduce to you a super important topic known as free body diagrams. So we're going to practice this and I'm going to explain it here, but keep in mind, every time you do a physics problem that involves forces at all, I expect you to sketch some form of a free body diagram, and I will take points away simply for you forgetting to draw a free body diagram, even if you get everything else right. It's a very important skill, and it's something I want you to get in the habit of. So let's imagine we wanted to draw a free body diagram for this car. So here's this car. It's broken down. These two guys are pushing it because they're out of gas trying to get to the nearest gas station. There's resistance from the road and from the gears on the car and everything since the engine's not on. So let's say that that has an opposing force of 560 newtons. And you can see apparently the guy here on the right is a little tougher than the guy on the left. He's applying 395 newtons. The guy on the left only 275 newtons. So what would a free body diagram look like for this situation? Well, what we would do is we'd take this object, represent it as a single point, and draw each force acting on the object and its direction. So for this car, I would take the car, represent it with a single black point, and say, all right, I know that there are 5 forces acting on it. The opposing force, the push from person 1, the push from person 2, as well, even though it's not labeled here, we know that it's in a car, so it has a weight force, the force due to gravity, and since it's sitting on the road or something, there's also a normal force in the upward direction. So notice, I label each of these 5 forces with their relative lengths for magnitude as well as the direction shown in the picture. So let's practice with some more free body diagrams. I'm going to show 3 pictures. After each picture, I want you to pause, try to sketch your own free body diagram, and then I'll show you what it should look like. So here's the first situation. Here you have a sprinter who's taking off. She's just beginning to run. As you can see, one of her feet is still in contact with the starting block. All right, so what would a free body diagram look like for her? Pause it and draw your free body diagram. So hopefully you got something that looks like this. For this runner, you can think of there really being two forces acting on her. One is her weight force going straight down, the force due to gravity, and the second is the contact force between her foot and the block. She's going to push backwards on the block, but the force on her is the reaction force of that, the equal and opposite force forward. So there's a forward force acting on her, but it's also at an upward angle. All right, so you can think of this as being partly a result of her weight needing to be supported as she's taking off, and also the forward thrust that she's providing herself with, kind of like an X and Y component of this one contact force between her foot and the block. All right, if you drew this as two separate forces, a normal and a forward thrust, that would be acceptable on this example. All right, here's another one that I just found. Here's two people playing basketball. All right, so you have one person, you can see he's completely in the air, so he's about to make a layup, and over here is the guy who's supposed to be playing defense, who looks like he's just being a spectator instead, standing off to the side, attempting to play defense. So pause it and try drawing a free body diagram for the person in the air shooting the basket, as well as the alleged defender. Okay, so hopefully you came up with something like this. For the guy making the hoop, guess what? The only force acting on him, if you notice, no one's touching him. It's strictly just his weight force. A lot of people are inclined to put, well, what about his jump force? Is he touching the ground? No. So his jump force has ended. The only thing carrying him up is actually his inertia. All right, so when he's in the air, if no one's in contact with him, the only force acting on him is his weight. And the spectator over here, the alleged defender, well, he has his weight force and the normal force from the ground as well, since he's still on the ground. All right, now here's one more. This one's a little trickier. I love scuba diving. So here we have a scuba diver. If you notice, her bubbles are moving kind of to the right relative to her. So let's assume she's swimming forward and she's staying at a constant velocity and a constant elevation in the water. So she's not moving up or down, all right, but she's just swimming horizontally. Pause it and draw a free body diagram for her. All right, so let's see what we got. For her, there's actually 4 different forces. All right, she has her weight force. Even though she's in water and floating, she still has weight force. She's still on Earth. There's still gravity pulling on her. There's a force opposing that, the force from the water making her want to float, known as a buoyancy force, going upward. She's going to be probably kicking with her fins to move forward at a constant velocity. All right, and I told you she's moving forward with a constant velocity. What does that mean about her net force? Well, it must be 0. So there's a force opposing her. In the water, we would call that a drag force. It's kind of like air resistance, but in water. All right, we can't ignore it like we do air resistance, because drag in water, as you probably know from personal experience, is much larger than that in air. So let's go ahead and start and practice looking at equilibrium situations, and then we're going to practice looking at non-equilibrium situations. So again, equilibrium means the net force is 0 and there's 0 acceleration. So sum of the forces equals 0, meaning both net force equals 0, forces in the x equals 0, and forces in the y equals 0. So it's really nice. When you have equilibrium, you really get 2 different equations out of that. One for the x direction and one for the y direction. All right? So keep in mind, sorry, one other side note, a lot of common misunderstanding is that when the sum of the forces equals 0 and there's no acceleration, you can still be moving at a constant velocity. Don't forget about that, all right? So when we go to try to solve some of these problems, the first thing you're always going to want to do is choose your object that you're going to look at, and the object that you're going to draw a free body diagram for, and the object that you're going to do some of the forces for. Determine whether or not it's in equilibrium. If you have an object in equilibrium, then you're going to start, just like before, draw a picture. In this case, it's a free body diagram, including all the forces like we just saw. Then once you do that, label x and y axes. Make sure you have forces all either in x or y direction. If not, you have to use vector components, break them into their x and y components, and then use your equations of equilibrium to try to solve. Set up some of the forces in the x direction, some of the forces in the y direction, and so on. All right, so we're going to do one equilibrium example. We're going to do a couple non-equilibrium examples, and then I'll let you practice the rest with homework and so on. All right, here's the first situation. I'm going to have you do this one all in variable form, no numbers, to practice the process. So you're helping an auto mechanic design the setup that he's going to use to support engines that he's working on when he extracts them from vehicles. So we have a situation where you have an engine here of weight W, and it's going to be hanging from 3 different chains as shown to keep it just a short distance away from the wall using this O-ring here that you see, this metal ring. So I want you to tell me how much force must each of these chains be able to support. Keeping in mind, all right, I want you to solve for the tension force in this setup in terms of W. That way, if the person whose garage this is has a different weight engine, he can calculate what strength of chain he needs in each situation. So solve for T1, T2, and T3 based on the value or the variable W, and then you can also see chain 3 makes a 60-degree angle relative to the ceiling shown. All right, pause the video, try it out. Make sure you paused. If you need a hint, here you go. Look at this, boom. Here's your free body diagram. Notice, I did 2 free body diagrams. You can do it for any object in equilibrium. You can solve using any different object. In this case, I identified 2 things in equilibrium. One is the engine, the other is this ring. So for the engine, I just have 2 forces, the weight going down, tension 1 pulling up. For the ring, I have 3 forces acting on it. I have T1 pulling down, T2 pulling to the left, and T3 pulling up at a 60-degree angle. So I labeled those 3 forces, and I noticed, following the steps that I just mentioned, that T3 is not in X or Y direction, but is rather at a 60-degree angle relative to the X-axis. So I went ahead and broke that T3 into an X component, T3 cosine 60, and a Y component, T3 sine 60. All right? So again, T3 got broken into X and Y components to make it easier to use my equation. All right, so let's go ahead and try to solve. So here's my free body diagram. I want to solve. I can choose to look at the engine or the ring. I'm going to choose to start with the engine because it's simpler. So if I set up some of the forces for my engine, I notice right away I have no forces in the X direction, so I don't have to worry about it. Some of the forces in the Y direction, it's in equilibrium, so it's equal to 0. So the way that I do this, on this side of my equation, I will add up all the forces in my picture. T1 is positive, W is negative. So T1 minus W equals 0. That's easy to solve. T1 equals W. Boom, box worthy. Already got the first tension. To solve for T2 and T3, though, I need to use the ring. So I'm now going to do some of the forces on the ring, following the same process. In this case, I have forces in the X direction, and I have forces in the Y direction. In the X direction, in the positive X, I have T3 cosine 60, and in the negative X, I have T2. So T3 cosine 60 minus T2 equals 0. I can solve and see, okay, T2 equals T3 times the cosine of 60, but I don't know T2 and I don't know T3. I need to find both of them, so I'm stuck. Ah, bummer. So I'll move on to the Y direction and see if maybe that helps. In the Y direction, I have T3 sine 60 up, T1 down, and so I do T3 sine of 60 minus T1, those are the only 2 forces, equals 0 because the ring is in equilibrium. Now I can try to start solving because look, boom, T1 equals W. So I can solve for T3 and substitute in W for T1. Look, that T1 just became W. Solving for T3, we find T3 equals W divided by the sine of 60. Look at that, box worthy again. I solved for T1 and T3. All I need left is to solve for T2. Now that I know what T3 is equal to, I can just plug it in. Look at that, boy howdy. Plug it in and I get T2 equals W cosine 60 over sine 60. I could box that up and call it good. I'm going to reduce, since I know sine divided by cosine is tangent, this is the same as W divided by tangent of 60. So that too is box worthy. So that's a good example. If I went a little quick for you, I recommend rewinding and just watching that part over again so you can understand that example problem. But it's a really good sample of the process. You must learn the process in order to be able to solve these problems. A lot of times too, I want to just reiterate and stress to you guys, a lot of times on these problems, people want to skip over steps in the process, skip the free body diagram, skip writing out all of the forces and things to just try to find the answer. When you do that, you make mistakes. Trust the process, trust the process, trust the process.
Oh yeah.
Oh yeah, as my wife just said, you might not have heard, she said, trust the process. Cool. So now moving on, let's just do a quick reminder. If we have a situation where objects are accelerating, then the sum of the forces does not equal 0, but instead equals mass times acceleration, which again, because of vectors, can be broken into x and y components. So let's try applying this now. I have two example problems for you. One is about one of my favorite things, which is hot sauce. So imagine you're sitting on a counter and somebody says, hey, pass the hot sauce. It's music to my ears, something I say all the time. All right. Yeah, that's true. My wife just said I don't actually have to say that because it's always sitting right in front of me. But maybe somebody else asked me to pass it to them. So I decide, okay, how fast do I need to push it in order to make it slide down the counter exactly 1 meter and land right in front of them? I do a quick mental calculation approximating the friction force, and I push it at 2.8 meters per second in order for it to slide exactly 1 meter and land in front of the person. So my question to you all is, what is that friction force that I approximated and was apparently accurate? So I push this bottle of hot sauce at 2.8 meters per second is what it's moving at as it leaves my hand. It slides 1 meter, stops in front of the person down the counter from me, and it has a mass of 0.45 kilograms. It's a substantial bottle of hot sauce, apparently. All right. What is the magnitude and direction of the friction force? Go. Oh, it's a good one, huh? All right, so let's see if you guys got it. This one's tricky, okay? Because I don't give you information about acceleration and forces and so on. I'm just asking you to find the force. Well, we know net force equals mass times acceleration, right? So if we look at our free body diagram for our bottle of hot sauce, as it's sliding, it has a friction force, it has the normal force, and it has the weight force. In the y direction, it's actually in equilibrium. It's not accelerating up or down. It's not flying off the table or crashing through the table. So in the y direction, it's in equilibrium. But in the x direction, the only force is friction in the negative direction, and that's what we want to find. And so if we go to solve this, we know that the net force equals mass times acceleration. So the force of friction here, F sub F is force of friction, is equal to mass times acceleration. The problem is I don't know the acceleration. I know mass and I want friction, but I don't know the acceleration. So at first glance, you might be like, oh, bummer, I'm out of luck. But we just finished talking about kinematic motion. We just finished learning how to find acceleration when we know things about velocity and so on. So let's go ahead and use kinematics to try to solve. We have a final velocity of 0, an initial velocity of 2.8 meters per second, a distance traveled of 1 meter. We can solve using our kinematic equation shown here. If we use this third kinematic equation, we can go ahead and solve. So let's do some algebra. Using algebra, I solve for acceleration. It's v final squared minus v initial squared over 2 times the displacement. Substituting in my values, my final velocity is 0, my initial velocity is 2.8 meters per second, and my distance is 1 meter. Solving for that, I find that my acceleration equals negative 3.92 meters per second squared. Wait a second, why is it negative? Well, it's accelerating in the opposite direction of the motion. So it's a negative acceleration, which is why we're going to have a negative force of friction. So if we take that acceleration and plug it into our force equation, force equals mass multiplied by acceleration, we can solve for the force of friction and find that it's equal to 1.76 newtons. Boom, box-worthy once again. So notice this was a different approach. We had to combine 2 different topics, motion and forces together in order to solve. Get excited, you're going to be doing a lot of that. Again, you must trust the process and draw on all the different tools that you've learned. All right, here's one last problem. I decided to ramp it up a little bit and give you a trickier problem here. So this one's Going to be tough, but I want you to give it a go. We have a situation here where we have a 10 kilogram block sitting on a flat, frictionless surface. All right, so let's assume there's no friction here. You got a 10 kilogram block here, and then you have a 3 kilogram block down here. Notice this rope that goes over the first pulley and passes around the second pulley here, it's the same rope that comes up here. So this is all one rope. Keep in mind, as we talked about, tension force is always the same at all points in a single rope. Notice that it's pulling up on this pulley here. You have the rope going up here and here, so it's going to be pulling up twice. Oh boy howdy. I want you to figure out what is the acceleration of the 10 kilogram block. I'll give you a hint. It's not going to be the exact same as the 3 kilogram block. Oh, tricky. And then also, what is the tension in the rope? Give this one a go. It's a tricky one. Hopefully you paused, and now I'm going to go ahead and solve it for you. So let's do free body diagrams. First, for the 10 kilogram block, what forces do we have acting on it? So first off, we have the weight of the 10 kilogram block going straight down. We also have the normal force from the surface of contact pushing straight up. And as we see here, we have the tension pulling to the right. All right, now for the 3 kilogram block, what forces do we have? Once again, we have the weight, we'll call it W2 for the 3 kilogram block going straight down. And we have tension pulling up on the left. And again, a second tension pulling up on the right. Because of that pulley, the string, or rope in this case, is pulling up on both sides. So you have the tension acting twice on the 3 kilogram block. So let's do some of the forces now. Let's start with the 10 kilogram block. Sum of the forces is going to be equal to mass times acceleration in the x direction, since it will accelerate to the right as a result of the string pulling it. So the only force we have is tension, so tension equals m1 times acceleration. But we don't know the tension and we don't know the acceleration, so we have to stop. Bummer, we're out of luck. So now let's move on to the 3 kilogram block. All right, I just decided to go ahead and show you some of the forces in the y also equals 0, but we don't need to worry about that in this problem because we're not asked to solve for the normal force or anything. All right, so for the 3 kilogram block, sum of the forces in the x is 0 because there are no forces in the x, that's easy. Sum of the forces in the y also equal mass times acceleration, but notice, this is a little tricky, right? It's going to be accelerating down, so I had to insert a negative sign to make sure we knew it's accelerating down. And also, it's going to be accelerating at half the speed of the 10 kilogram block. So it gets double the tension because the string is moving up twice, but it moves at half the acceleration for the same reason. All right, and if you're not sure about that, go ahead and make your own little experiment with the pulleys in the lab kit, and you'll see the exact same thing. All right, so net force equals mass times acceleration, but it's accelerating down, so it's negative, and it's half the acceleration of the other block. So sum of the forces, we have T going up once, T going up twice. We have negative weight, which is mass times gravity is weight, equals m times negative 1/2 a. So from here, if we look, we don't know the tension and we don't know the acceleration, but we have two equations, both with tension and acceleration as unknowns. So guess what? We can solve system of two equations. We're going to plug this tension in to our other equation. Not once, but twice. So now, instead of having 2t, we have 2m1a, since that's what tension is equal to, 2m1a minus m2g equals m2 times negative 1/2 a. And look at that, boy howdy. Acceleration is our only unknown, so we can use algebra, do some solving for acceleration, so get our accelerations together, factor out acceleration and divide, and you find that acceleration is equal to the weight of the 3 kilogram block divided by 2 times m1 plus 1/2 m2, keeping in mind m1 is 10 kilograms and m2 is 3 kilograms. So we plug and chug and do the math, and what we find is that we get an acceleration of 1.37 meters per second squared. And now we got the first half, part A, done, but we need part B still, the tension in the rope. So what we can do is we can take our equation up here for tension. Oh, sorry, acceleration box worthy. Boom, nailed it. Now we can take our equation for tension up here and substitute in the newfound acceleration. Tension equals m1 multiplied by acceleration. m1 is 10 kilograms. Our acceleration we found to be 1.37 meters per second squared. Plug and chug, and we find that the tension is a box-worthy 13.7 newtons. So, pretty good and tricky example problem here, huh? Let me know if you have any questions, but that wraps up the end of Chapter 5. Have a box-worthy day.